Hello, my amazing pre-IB students. Welcome to your new online version of our pre-IB class. I hope everybody's doing well. Remember, you can always access some of the things we've practiced in class with our mindful minute whenever there's a little bit of chaos or discomfort. You can always take a moment to just close your eyes and come to your breath and your body to remind you that right now, wherever you are, is the only moment you can control. With that being said, this is our first video lecture. I'm going to be lecturing lecture 21 from Unit 3. And so those slides will be online, as well as the work that is going to be assigned to you at the end. So all right, let's just get into it. Here is your bell ringer. What is the name of Ag2SO3? Well, first, I'm going to look here and notice that this is a metal, and it's a special metal because it's a transition metal. So that means something. It means that I can't just write its name. I have to write its name and a Roman numeral. The name of Ag is silver. So I know that part so far. And just bear with me with writing with this. Not really used to it, so here we go. Okay, silver. Silver something, though. And we're going to figure out what that something is and put it in these very nice parentheses that I just drew. And so now we're going to look at SO3. SO3 is sulfite. Sulfite with an I. Oh my goodness, okay. You get the drift here. And so you might remember that sulfite has a charge on it because it's one of your polyatomic ions. And that charge is 2 minus. So since this SO3 doesn't have any parentheses around it, that means that there's only one of them. And one, I'm going to put parentheses here, 1 times the 2 minus charge on this molecule means that there's an overall -2 charge inside of this compound. But we know that ionic compounds are neutral, meaning the charge has to equal 0. So that's where the positive part comes in here with silver. According to this formula, there are 2 of these silver atoms. So 2 times something, whatever the charge is on this atom, or on this ion, has to equal +2 in order to cancel out the -2 charge. So 2 times 1, right? 2 times 1 would equal +2. So +2 and -2 cancel out. This is silver 1. There are 2 silvers. They each have a +1 charge. There's only one sulfite. It has a -2 charge, and therefore it cancels out and the charge equals 0. Good job. All right, we're moving on to a new type of bond, the coordinate covalent bond. We've learned about single bonds, double bonds, and triple bonds. In a single bond, 2 atoms were each sharing 1 electron with another. So for instance, here is a molecule of hydrogen, H2, hydrogen. Each of them share their 1 valence electron with the other, and so you get a single bond, meaning each atom is sharing 1. There's a total of just 2 electrons being shared, single bond. A double bond is, for instance, what exists between an oxygen molecule, meaning O2. Oxygen has 1, 2, 3, 4, 5, 6 valence electrons. 1, 2, 3, 4, 5, 6. And so I can do this right here and this And now I've made a double bond. Double bond means that each atom is sharing 2 electrons with the other atom. You have an equal sharing. This oxygen shares 2, this oxygen shares 2 back. They each together then are sharing 2 pairs, which makes a double bond. Here, there was also equal sharing, but each atom was only sharing 1 electron with the other. In a triple bond, a great example is nitrogen gas, which is N2. We have 2 Ns. Each of them have 5 valence electrons. And so you can see where I'm going with this. They're each going to share 1, 2, 3 with each other. 1, 2, 3. And so that makes 3 pairs of electrons, making a triple covalent bond. Our other type of bond is coordinate, and you see this little arrow here. So let's learn about it. Here in this example is carbon monoxide, which by the way is extremely toxic. That is why we don't want people idling in their cars and releasing it from their engines. Here is carbon with its 4 valence electrons, and here is oxygen with its 6 valence electrons. So here I see that I can make a bond, perfect, and here I can make another bond, perfect. So now there's a double bond, and O has 1, 2, 3, 4, 5, 6, and feels like it has 7 and 8 valence electrons since carbon is sharing with O. And O is sharing back with carbon, so carbon has 1, 2, 3, 4, 5, 6. Carbon has not yet reached the octet rule. Carbon needs 2 electrons in order to actually have the 8 that it needs to be stable. The problem is if carbon shares with oxygen, it is going to give oxygen too many electrons. Oxygen has already reached the 8 that it needs. Carbon is the only one that needs electrons, and it needs 2 specifically. So remember that we're never going to break up couples, right? We're not going to be those people. We're going to leave couples happily together. But what this couple here, this lone pair here on top of oxygen is going to do is it's going to share itself with carbon as well. So this lone pair, we call this a lone pair of electrons because it's a pair of electrons that's just here alone because it's nice and happy in its orbital, is up here on oxygen. This lone pair is belonging to oxygen but also being shared with carbon. Carbon now feels like it has 1, 2, 3, 4, 5, 6, 7, 8. Oxygen still has 8 because these 2 still belong to oxygen. So 1, 2, 3, 4, 5, 6, 7, 8. And it's not receiving anything back from carbon, so everyone is happy. Basically, you're going to use a coordinate bond whenever you feel like you've done the molecule incorrectly or you're missing 2 electrons. So if you keep trying to do what you usually do and it doesn't work out, then go ahead and try to do the example again using a coordinate bond. Let's use SO2 as an example. S has the lower electronegativity value between S and O. And I know that from the trends of periodicity. So if we look at a periodic table, we could remember that electronegativity increases across a period and decreases down a group. That means that if it increases across, then O and S, they're in the same position. So I'm not sure yet who's stronger, but it decreases down. Therefore, S has a lower electronegativity value than O, and it goes in the center. As I put these valence electrons, though, remember that carbon, regardless of electronegativity, will always go in the center. And hydrogen, because it's so small and can only make a single bond, will never be in the center. It will always be on the side. So here's S, and so I know S is going to hold these two O's. So I'm going to put one O here. 1, 2, 3, 4, 5, 6. And I'm going to put the other O over here. 1, 2, 3, 4, 5, 6. Now I'm going to make a mistake, okay? I'm going to bond here and here because I know that I have to bond the two O's to the S. But what is wrong now? Take a look for a moment. You got it. The S has 1, 2, 3, 4, 5, 6, 7, 8 electrons now. The S is done bonding, but the two O's do not have the 8 electrons they need. Therefore, this is a hint to me that what I need to do is access a coordinate bond. They both, the oxygens, need 2 electrons. So what I'm going to do is make a bond here and a bond here. This makes a double bond. D for double, okay? This makes a double bond here. Now this O is complete and so is the S. This oxygen is like, what about me? And it's just here on the side waiting to be bonded. The S doesn't need any more electrons, but it will share its lone pair. And I'm going to show that with an arrow. So when I draw this arrow, I'm showing that S is being very nice and sharing its pair with oxygen. And so oxygen now has 1, 2, 3, 4, 5, 6, 7, 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8 for S, and 1, 2, 3, 4, 5, 6, 7, 8 for O. We are complete. There is a double and a coordinate bond. One double, one coordinate holds this SO2 together. Let's do the same for SO3 and O3. S in the middle because it has the lower electronegativity. The O's on the side, and remember, O's do not bond to each other, so you're never going to make triangles. Oh my goodness, my O's come out terribly. 4, 5, 6. I'm going to make a double bond here and coordinate. Whoop, okay, that was an arrow. And coordinate. So this S has a double bond with the O down here. This S has a coordinate bond with this O, and the S has another coordinate bond with the O over here. This is the lone pair. Oh my God, let me redo that. This is the lone pair here that this S is sharing with oxygen, and this is the lone pair here that this S is sharing with oxygen. Okay, let's do that with O3 now. O3, by the way, is ozone. So it is what makes up the ozone layer, whereas O2 is the oxygen that you and I breathe. Here's one of the oxygens. Now notice these oxygens are bonding to each other, but that is because they have to. This is an element. It's only made up of oxygen. So in this case, we will bond the oxygens to each other. Now I'm going to make a mistake again, okay? Just so we can see how we might get stuck, but be able to get ourselves out of the problem. I'm going to bond here and I'm going to bond here and be like, voila, I finished. But what is wrong with what I just did? Take a moment to look. Exactly. All the oxygens on the side here are not complete. The central atom has 1, 2, 3, 4, 5, 6, 7, 8. So central atom is like, I'm good. Okay, that's a smile. And these side oxygens are not happy. 1, 2, 3, 4, 5, 6, 7 only. This one has 7 only. 1, 2, 3, 4, 5, 6, 7 only. Oh no. These oxygens are not happy. So what can we do instead? We can recognize that really we're in a bind unless we remember that we can use coordinate bonds. So I'm going to circle here and make an arrow over here. And now this oxygen has 1, 2, 3, 4, 5, 6, 7, 8. Perfect. This oxygen has 1, 2, 3, 4, 5, 6, 7, 8, because remember, these still belong to the one who is sharing them. This oxygen has 2, 4, 5, 6, and now 7, 8. So we have created a molecule with one coordinate bond and one double bond. Nice job. All right, moving on. Polyatomic ions. Ignore that it says bell ringer. This is just new stuff. Do polyatomic ions contain ionic or covalent bonds? Well, let's consider they are ions, right? Like they have these charges on them. 1 minus, 2 minus, 3 minus, plus. But if you look inside the molecule, N and O, for example, are nonmetals. O and H, nonmetals. HCO, nonmetals. Everything here is a nonmetal. That means the answer is both. The molecule itself is covalent. So the O bonds to the H with a covalent bond. Everything in here bonds covalently, either single, double, triple, or coordinate bonds. But any of these ions can bond to another ion ionically. An example being, for instance, if Mg, which is a metal, 2 plus, loses 2 valence electrons because it gives it to, let's say, sulfate, right? So 2 minus. That means that now sulfate, which is covalently bonded, can bond to magnesium because magnesium is positive and sulfate is negative. So they will bond very romantically, ionically, but the sulfate itself will bond covalently. Just know that because it might be a multiple choice question asking you which of the following compounds contain both ionic and covalent bonds. You'll want to look for a polyatomic ion that is bonded to a cation or anion. We're going to move on to now looking at polyatomic ions and bonding them. We're going to draw them and say what types of bonds they have. Coordinate bonds will definitely come in handy here, so keep those in mind. Let's look at nitrates. Between N and O, nitrogen is in the middle because nitrogen has the lower electronegativity. Let's redo that. So that's 1, 2, 3, 4, 5. The oxygens are going to all bond to the nitrogen. So I'm going to surround nitrogen with the oxygens. And I'm going to see what types of bonds I can make. Oops, let me redo that. And actually, let me do it down here. So once again, what I'm going to do is make a mistake, okay? I'm going to go 1, 2, 3. What is wrong here? You're right. The oxygens all have only 7 electrons. So what I can do instead, oops, wrong button. What I can do instead is bond one of them with a double bond. Leave this one with a single bond. And then maybe move this one so that it is on top of the lone pair. 1, 2, 3, 4, 5, 6, because then I can access a coordinate bond. I can use this to give it the 2 using the coordinate bond. That was terrible. Let's do it this way. Here we go. So here's my arrow. This oxygen is receiving these 2 because nitrogen is sharing it. So now we have 1, 2, 3, 4, 5, 6, 7, 8 for this oxygen. Check mark. Good job. This oxygen has 2, 4, 5, 6, and then 7, 8 from these 2 being shared. The nitrogen still has these 2 plus 3, 4, 5, and then 6, 7, 8 being shared from the other oxygen. So the nitrogen is also good to go. This oxygen, though, only has 1, 2, 3, 4, 5, 6, 7. But look at the charge. This nitrate ion has 1 electron on it. That actually means that we're going to draw brackets around the structure. We're going to put a negative on the outside to show that there's an electron being taken from the atmosphere or taken from somewhere else. And we're going to add it wherever it's needed. And I know where it's needed. It's needed right here. So there, I've added it in, and now this oxygen is happy. Basically, now you can see why polyatomic ions are the way they are. They pick up electrons or they lose electrons from areas so that they can be complete with their octets and they can feel stable. This oxygen needed an electron, therefore the molecule has already gained one. Checking out what's written here. Make sure to add in an electron for each negative charge that is on the polyatomic ion. If it is a positive charge, you are not adding an electron, you're taking one away, and we're going to practice that with letter B in a moment. And make sure at the very end that you've put the Lewis structure in brackets and you've written the charge on the outside. It is required, and the question is wrong if you answer it without brackets and without the charge on the outside. So let's move on to NO+. I'm going to use the next slide where you see some answers. NO+. Here's N. And here is O. I see I can go like this and like this. Oxygen now has 1, 2, 3, 4, 5, 6, 7, 8. Nitrogen has 1, 2, 3, 4, 5, 6, 7. The molecule says that it has a plus charge. So what we're going to do is take away an electron, and I'm going to choose to take away that one since nitrogen is the one that I have incomplete so far. So now I put brackets and a plus sign to show I took one away, and I recount. So 1, 2, 3, 4, 5, 6, 7, 8. Oxygen is complete, nice and happy. N has 1, 2, 3, 4, 5, 6 only. What do you think we should use in order to complete it? A coordinate bond. We're going to share a coordinate with nitrogen so that now it has 1, 2, 3, 4, 5, 6, and the 7 and 8 from oxygen. Remember, these still also belong to oxygen. Oxygen is just being really nice about sharing its pair with nitrogen. If we had not removed this electron from nitrogen, nitrogen would have either remained with just 7 and been unstable, or it would have had 9 because we would have tried sharing something from the O to complete it. Therefore, it takes these 2 from O and it removes the electron. Now, you might be asking, do I have to remove the electron from nitrogen? No, you can definitely remove it from oxygen as well. And both structures would be correct. So if you answered it this way and someone else answered it the other way, that's fine. You would both have a correct answer. So let's draw 1, 2, 3, 4, 5, 6. And let's decide to remove one of the electrons from oxygen. Let's remove that one. And let's put our brackets. And the plus sign. And now let's see. 1, 2, 3. Perfect. Oxygen has 1, 2, 3, 4, 5, 6, 7, 8 electrons. Nitrogen has 1, 2, 3, 4, 5, 6, 7, 8 electrons. We are happy. We are complete. These are 2 ways of solving, and they're both correct. Notice that even though this one is comprised of a double bond and a coordinate, at the end of the day, it is the same as this triple bond. This is a triple because there's 3 pairs. This is really a triple at the end of the day because there's 3 pairs of electrons. Even though one of the pairs comes from oxygen, that doesn't really matter. 1, 2, 3. Therefore, you could still say this is made up of a double and a coordinate, or you can say it's made up of a triple bond and you would still be correct. This one, you really can only say triple bond because there's an equal sharing of 3 electrons from each atom. All right, last one, NO2 minus. And in the middle, lower electronegativity. And now let's put the O's on the outside. And keep in mind, there's definitely going to be a minus added here. Meaning an electron added into the molecule. But first, let's just draw it like we normally do and then see what's going on. I'm going to pair these and I'm going to pair these. And now I'm going to just take this one and pair it here. So this is 1, 2, 3, 4, 5, 6, 7, 8. This oxygen is complete. 1, 2, 3, 4, 5, 6. Whoops. 1, 2, 3, 4, 5, 6, 7, 8. Also for the nitrogen, so nitrogen is complete. This oxygen only has 1, 2, 3, 4, 5, 6, 7. However, the molecule says that it adds an electron in to make it stable. So I'm going to add it here where it's needed. And now this oxygen has the 8 it needs. What you can also do, and I'm sure some of you have figured out, is you can add the extra electron to the nitrogen. So let's start all over again for NO2 minus and put 1, 2, 3, 4, 5, and let's just already put 6, okay? And now let's add our oxygens. So 6 means I added this extra one already to the nitrogen. So here's oxygen with its normal 6 valence electrons. Here's the other oxygen. And I'm going to put my brackets and the minus because I already added the electron to nitrogen. So I'm going to do 1, 2, and now because I added it to the nitrogen, I'm able to do a coordinate bond. And everyone is stable. We have 1, 2, 3, 4, 5, 6, 7, 8 for that oxygen. The nitrogen, 1, 2, 3, 4, 5, 6, 7, 8 for this nitrogen. This oxygen, 1, 2, 3, 4, 5, 6, 7, 8. Everyone is complete. In this one down here, we said double and single. And here we have double and coordinate. And a coordinate bond is really just like a single bond because it's still just 2 electrons being shared between 2 atoms, just like here. So both of these would be correct. Now this here is your practice. You're going to find this on Google Classroom. The Google Classroom assignment is going to have these exact molecules, and you're going to be drawing them and stating the bonds that are present. You're going to then upload a picture of your assignment to Google Classroom. All the instructions for this assignment are already online. They're going to be found on the assignment. That is where you'll see the directions for this assignment. These two here, these are challenge molecules. I do not expect you all to get it right away. I do expect correct answers for these here. Your assignment is going to be due by 9 a.m. on Wednesday the 18th. That means that by 9 a.m. Wednesday the 18th, that assignment will close and anyone who hasn't turned it in will be receiving a Z. Late work will not be accepted, particularly considering our circumstances. You can reach out to me via email or Google Classroom. If you want to email me, that's eliza.hiley@gmail.com. Remember that past 5 p.m., I am most likely going to be answering you the next day. So don't leave this for last minute if you can. Thank you so much for listening in. I hope you were able to understand. Do your best, do it on time, and contact me if you need anything. All right, guys, with that, go Cavs.
Mr. D's the best.
Okay, that was Mr. D.
Mr. D's the best.
Oh, my God. Okay.